Hello, I am Linzhou Zhou, the first author of this paper. I will present our work on perceptual similarity for measuring decision-making style and policy diversity in games, which discuss how to measure the similarity of decision-making, and we refer to as playstyle similarity. If you do not have time, let's have a brief introduction of this paper here. The problem of this research is focused on how to define and measure the style of decision-making, or refer to playstyle. For example, in playing a video game, I may want to play with my strategy, and others may want to play other strategies. Then these strategies can demonstrate different play styles. One solution to measure play style is directly compare the distance of action distribution from two playing resources. But how to model in the policy or identifying cases that are comparable? One previous work, playstyle distance, proposed first converting oscillations to discrete states and finding intersection samples, and calculating the policy distance over these intersection states. That is the first unsupervised end-to-end playstyle measure, and we try to improve this in this paper. We propose three enhancements, including using multi-scale analysis to leverage states with different granularity. Next, we discuss the relationship of distance and similarity from psychology aspect and human cognition. Finally, we incorporate the idea of intersection over union ratio in collection comparison to further improve the efficiency of discrete playstyle measure. We use several game platforms to test our measures, including some racing video games, Atari games, Game 2048, and the board game Go. We can achieve over 19% accuracy in playstyle identification task in all these games. In the following, I will try to introduce the paper in details. If you are busy or already get what you want to know, you can skip the latter part. Okay, this is the paper information. Our paper has been accepted for our publication in a TMLR. It's a long submission from August 2024. The authors of this work, including myself and my two advisors, Qiu Chen and Wu Chen, in National Jiaotong University, is called NCTU before in Taiwan. Today's storyline starts from discussing what playstyle is and its applications. Then, we will introduce available methods for playstyle measurement. Next, we will delve into our methods that provide new insights for improving playstyle distance, the end-to-end unsupervised playstyle measure. Then, we will conduct our experiments across several games to evaluate our new measures. Additionally, we will introduce an application of our method for defining the diversity of the reinforcement agent. Finally, we will conclude our findings. Now, let's start our story. So, what exactly the playstyle is, and why we should study it? Furthermore, what applications are related to the playstyle? Let me give an introduction. Playstyle is a decision-making style, and particularly in games. It represents different preferences in decision-making, such as unique strategy or characteristic displayed by players. In human behaviors, topics like diversity, individuality, and creativity are very close to playstyle. These are inherently related to distinguish different decision-making styles. If we can separate different styles, then we can define these topics. With this concept of playstyle, you may already come up with that it's important to decision-making problems. There are two major objectives in decision-making, including achieving optimal performance, aka exploitation, And we have witnessed several successful results with deep reinforcement learning these days. Another objective is about the pursuit of diversity, or referred to exploration. Although we may usually say improving diversity to improve agent strength and efficiency, or generalize agent across several tasks. But how we quantify this diversity? Looking at a better scan score, or checking the state distribution using TSME? It's possible, but it's not simple to directly quantify the actual diversity, since we have to define the diversity first, and it's especially hard in environments without built-in features. But don't worry, we will discuss the solution later. If we know how to define and measure play style, then we can improve many applications such as player modeling or analysis. We can measure the diversity of decision making for both human players and AI agents. Based on this measurement, human-like AI behaviors can now be more tangible. We can collect human records and track agent similarity to these records. Additionally, there are many other possible applications like understanding player preference or verifying identity and so on. Now, let's take a closer look at the methods for play style measurement. There are several approaches from heuristic rules and game features to supervised learning, unsupervised clustering, and contrastive learning. However, our focus is on method known as discrete play style distance, since it is the first unsupervised end-to-end measure with a clear meaning definition. For heuristic rules and game features, they are the most common method, like kill counts damages in a shooting game. Then what can it provide? Actually, anything you want. And what's the performance? It can be most precision for a dedicated study. The problem is that how to get it. It's usually expensive, since we have to manually engineer for each case, and it is domain specific. If there are many styles, or the style is unclear, then this kind of method may be hard to implement. To use these heuristics, machine learning can help. Supervised learning is a solution to classify playstyles, but it requires predefined labels and may not handle styles not present in the training set. Another method, like data mining techniques, unsupervised clustering, may help identify some interesting or different styles without explicit style labels. But the semantic meaning of this resource may not be clear. Taking a racing game as an example, it's common that different racing tracks have different backgrounds, like sea, forest, or city. But is that related to the driving style of players? Maybe not. But this unsupervised measure can focus on these factors. Also, we can use contrastive learning, like behavioral style measurement. It is a measure for playing chess measurement. The idea is that we can just identify myself group and not myself other groups rather than a clear playstyle label. So it's simpler and more general to supervise learning. But it still needs some record with identity, and it may not be clear to the case if one player want to perform several play style, or many different players may also perform the same play style. This is not a contrastive learning can handle. So if we want a more well-defined measure, then we can look at the similarity of action distributions. It's common in reinforcement learning to calculate the entropy or policy divergence if we have a parameterized policy. But how if we do not have this policy, like the case in analyze human players? We will not have a policy model, or even how to guarantee a state is comparable of two policies. The policy may be not defined in one policy or not well trained for some states. So, to address this problem, discrete playstyle distance is a solution. We can use discrete representations to identify some oscillations that is very similar in raw oscillation and very similar with very similar gameplay paths, and to assign they are the same state, and using intersection operation to get those comparable states. The action samples on these states are more comparable, and we can define the playstyle over action distribution. But this kind of method requires a decent discrete state encoder to have a good accuracy. In the playstyle distance, there is a hierarchical state discretization, HSD, to get a flexible discrete encoder. It is a hierarchical variant of VQVAE, the popular discrete representation with neural networks. See the figure? There are two gameplay resources, including oscillations and corresponding actions. For example, the oscillations in A are discretized into the discrete states, and also the oscillation from B also discretized to discrete states. Then we can find the intersection of these two state sets. After that, we can calculate the expected action distribution distance over these intersection states, and that is playstyle distance. To have a more formal definition, we have a playstyle dataset MI, sample from the style I, including many oscillation and action pairs. Also, a pre-trained discrete state encoder phi. For training this encoder, we do not need the playstyle label. Just use some oscillation and corresponding actions to train them. They are sufficient to learn how the game state look like. And the train data only from single style is sufficient to many styles. And for each state as encode from the phi, action distributions are deduced using a sampling distribution. Just average the action samples for a policy distribution. For comparing two action distributions, we can use W2 metric, Western distance, where is the effort defined on CDF, then moving one probability distribution to another. The playstyle distance is defined as the average of expected action distribution distance over the intersection states. Now, let me introduce the new insights to improve playstyle distance. The first part is about using multi-scale states. Playstyle distance needs a proper discrete state space. If a discrete state space is too large, we cannot get intersection states. If too small, we would lose some important information to separate those non-comparable states. Furthermore, some ambiguous states may need to collect many samples, to have a better action distribution with more precise distribution, which is requiring at least T samples on a state from two comparing datasets. That's for T equal to 2, then for a given intersection state, for one dataset, you have to have two action samples on that state, and for another, you also have two action samples on that state. So, how to select the discrete state space? Let's think about how humans do, since humans also do case-by-case assessment. In human cognition, we perceive similarity on a convergence of multiple attributes, leading to a holistic understanding. Thus, an observation sample has many attributes or states, from a broad view to intricate details. Then, why not we use all available space if we have? We transfer the discrete state function phi into a mapping big phi. It is an ensemble of mapping functions. Very straightforward. And we can get this mapping from either training several encoder or the HSD encoder also provide several mapping inherently. Then we can reinterpret place-style distance to a multi-scale version. It's very simple. Just the uniform average of distance from different state space. Our experiments show that when using multi-scale state, we do not have to care about the sample threshold T. This is because it can dilute the impact of outlier during distance computation and leverage more useful details. Thus, the trade-off between small or large state space is alleviated. Let's have a parent preview on the racing game Tours. There are 25 reference play styles, and we have to classify the source style of a given query dataset. If the discrete state space is 1, taking every observation as the same, the accuracy is bad. If we use the space 2 to the power of 20, as suggested by the original paper playstyle distance, we can have a decent accuracy, especially with the sample threshold T equal to 2. If we further use the very large state space, it's not reasonable to have a sample threshold with few intersection samples. When combining all these three state spaces, we found that it has the best accuracy, and even no clear difference with threshold 1 or 2. Now we finish the first enhancement, multi-scale state. The second enhancement is about the perception of similarity. Although it's common to use a negative distance to describe similarity, we argue that it's not meet the intuition of human. For example, there's a point T. There are many points have the same distance to T. As the distance grows, the candidate circle also increases. This is about the degree of similarity. As distance grows, the distinction becomes bigger. The phenomenon was found on humans about magnitude effect, which humans diminish sensitivity to larger numbers. In line with Weber's fractional law, in psychophysics, where the relationship between stimulus and perception is logarithmic as the magnitude of stimulus increases, sensitivity diminishes. Thus, we propose incorporating the idea of higher sensitivity to smaller distances into our placestyle measurement. Also, we want to use a probability to describe similarity like meet human intuition. In the main paper and appendix, we use the property of probability and Weber fractional law to derive a perceptual kernel function that maps distance similarity to a probabilistic similarity, and it is the exponential kernel. If you are interested in this derivation, please check out Appendix A1. This perceptual kernel can be found in several places. For example, in the radial basis function RBF, and also in the transformation between bacteria distance and the coefficient. Bacteria coefficient is a similarity measure between two probability distributions P and Q, and it is related to the overlapping region between these two distributions. In placing style distance, it suggests that using W2 distance of action distribution, and it can be explained as the effort, physical or even mental effort, to change their action distribution, and is from a player role. In another aspect, bacteria coefficient can be explained as the observer role, where an observer cares about the occurrence of action outcomes, and player may care about the effort of action distributions. Incorporating the precision kernel into multi-scale playstyle distance, we can change the distance average process from expected version to a uniform version. This change not only streamlines calculations, but also underscores the significance of encoded granularity. If two observations are very similar, they should have intersection on several state space. If not so similar, they will only have intersection on some small state space. If they are not similar, they will not have intersections. Besides, to meet our probabilistic framework, the action distribution distance has to be 3-scale with a constant to ensure the expected distance converge to 1 before Perceptual kernel. If you want to use bacteria coefficient directly, they can skip this scaling part. This is the second enhancement, perception of similarity. They change a distance value to probability to meet the intuition of human about similarity. Imagine that you say people A look like people B, and their distance is about 0.5. There's no idea about the similarity directly by the 0.5. It's not clear. But if you say that people A look like people B about 80 similarity, it's more clear since you can image that there should be some part of these two humans, and we can image that how they are be similar. Finally, we have the third enhancement of discrete playstyle measures. In playstyle distance, we only consider intersection of states for comparable cases. But what if intersection samples are limited or with small intersection proportion? It may be unstable or insufficient sample for measuring playstyles. A small intersection could indicate two scenarios. One, distinct state-within distribution, and it might just signify different playstyles. Two, some uncontrollable factors internal to the playstyle happened, such as environmental randomness or the decisions from other players in a multi-agent game. And we need for more sampling to have a better accuracy. But for further approach to improve the efficiency, aka using this sample to have a good precision, we can consider the proportion of intersecting samples relative to the total observed samples, and that is Jacka index, or so-called intersection over union. It is a prevalent similarities measure in collection comparison. This called intersection over union can serve as an effective playstyle measure under some specific condition where game observations are clearly delineate playstyle distinctions. However, the theoretical fails in some cases that states recur due to game rules or even every state is visited. In that case, it is impractical to measure playstyle solely from observations. But despite its potential limitation, our empirical finding suggests that the Jacka index serves as a handy measure when the state space is large and the randomness in the game is low. Also, the measure is simple as this equation. intersection over union. Combining these enhancements, we have a comprehensive playstyle measure, playstyle dissimilarity. Thanks to the uniform average of states, playstyle similarity can be understood as playstyle Jacob index multiplied playstyle intersection similarity. Jacob index assigns a uniform weight of 1 to each intersecting state, regardless of the similarity between the action distributions. Playstyle similarity infuses a probability-based weighting that alleviates the potential limitation of Jacob index. Also, it has some good properties like a consistent interpretation of zero value, that's infinity distance. Besides, the original playstyle distance cannot directly be incorporated with the Jacob index due to its nature as a negative similarity. Then, we can have an overview of playstyle similarity. Start from playstyle distance, and then we first introduce multi-scale states. And second, the procedural kernel to emulate human cognition. Finally, an intersection over union operation further leverage the overview of all observed samples. That is playstyle similarity, a new end-to-end unsupervised playstyle measure we proposed. We have many experience to support and analyze our measure, but we only check some results here. For more detailed results, please directly check the main paper or even the appendix. We conduct the evaluation on various game platforms and several player types, including 2 racing games, 7 arcade games, the puzzle game 2048, and the board game Go. For player types, we have role-based AI, human player, and deep reinforcement agent. Also, the action space, including continuous action and also discrete actions. Our dataset and discrete encoder follows previous paper with official release. We also plan to release our new code of this paper. In our video game experience, we will have 3 levels of discrete state space, from the most small space 1 to a very large state space that provided by the previous paper. We use different similarity measures to perform the zero-shot playstyle classification. For example, there are 4 playstyles. We random sample a dataset from a style, including many observation action pairs, as the reference dataset. Then we have a dataset sample from an unknown playstyle and try to use the similarity measure to identify its playstyle and count the average case accuracy. We focus on the evaluation on video games in this presentation and check the performance of our 3 enhancements. First, for multi-scale state space, we already know it is effective on the racing game, Taurus. In another racing game, GSK, some playstyles are related to keyboard actions, like drift or natural acceleration, and it can be captured even with only 1 state space size. For Atari games, the 2 to the power of 20 state space is good enough. You can see that in different cases, we need the proper discrete state space setting to achieve the best accuracy. But what state space is the best is a question before our evaluation. So, using our multi-scale state space without a sampling threshold is a handy and general solution to get the best accuracy. Next, we want to know whether the probabilistic similarity can have the same or even better accuracy to the negative distance similarity to meet the human intuition. The result in Taurus with continuous action space is clear that new method is better. For another racing game, with discrete actions. It's not very clear, but there is still some accuracy improvements. This resource verifies that probabilistic similarity is a good alternative to negative distance similarity. Also, for the x, it's about the size of a sampled dataset. For example, we use just 2 observation action pairs to perform the classification. And for this case, we have around 1,000 observation action pairs to perform the classification in a row. Finally, combining all of these enhancements, including multi-scale state space, perceptual kernel, and Jaka index, we can compare all discrete playstyle measures here. Notice that we also upgrade the playstyle distance to the same multi-scale version. The purple and brown curves are good on TORS and RGSK. Also, using Jaka index only, the red line still suggests it's a decent measure, better than playstyle distance. And the shaded area is about the mean and the max accuracy in the 3 different encoder models. In Atari games, we have individual resources for each game in the appendix. Here, we combining all games to a single scenario Atari console. Since all games on Atari game platform can share the same observation and action scheme, thus merging all games to one game is possible, just like we only play the Atari console with different game content and it's only one game. Therefore, we will have 1 plus 14 discrete state encoders, including a single state space mapping and 2-level discrete encoder for each game. There are 7 games. The resource still reports playstyle similarity and its bacteria coefficient variant are the best. Now, we already know that our new playstyle measure is the best discrete playstyle measure. Also, it's more general to any supervised or contrastive methods since they require some playstyle identification or label. In the case without playstyle identification or playstyle label in the training data, like our experiments, those methods are just like a random guess since it cannot be trained with the label or identification. There's no. Then, is there any unsupervised and end-to-end methods in playstyle measurement can be compared? We know that style in generative models is a popular topic. We may find some baseline from that. In generative styles, the measures are usually based on a well-trained ImageNet classification model, like Inception. The popular basic Inception score is not proper to playstyle since it detects how an image looks like real or fake. But in playstyle, all observations are provided by the game environment and all observations are real. Another popular measure, suggest inception distance (FID), is a valid measure and also common in generative styles. Its idea is based on checking the distance on the latent feature of image. Then, let's using the continuous latent features to get the latent distance in our gaps. Since playstyle Jaka index only see the observation can have decent performance, then latent feature should have sufficient information to playstyle. We can compare the mean vector of observations with either Euclidean distance, L2 distance, or cosine similarity. In TORS, it's just like random, since the observations are very similar in that game and cannot be clearly separate on the latent observation space. In contrast, RGSK and Atari console, they can have better accuracy, but playstyle similarity is still better, since it's clearly defined on the action distribution, not solely on observations. If we check more detail on each Atari games, we found that latent similarity is only better than playstyle distance. On two games, this resource suggests that if you want to use latent similarity for playstyle, it may be dangerous, since we do not know what playstyle it will capture. In contrast, discrete playstyle measurements are clearly defined on action distribution and conditioned on those comparable states. Now we have a good playstyle measure. Then we can define the diversity of agents in deep reinforcement learning. Then how to quantify the diversity of a player policy? The idea is very simple. If a new trajectory is not clear, it's not very similar enough to any other trajectory, then we can count that it's a different one. We can assign a probability similarity threshold like 20% and check the similarity of a new trajectory to all previous trajectories to quantify the diversity. If you are interested in this part, we have some experiments in the paper to support this idea. Finally, we conclude this paper. This paper proposed 3 techniques to enhance discrete playstyle measure, adopting a multi-scale state space to help the selection of a proper discrete state space. Also, using perceptual similarity rooted in human cognition to provide explanations of similarity that meet human intuition. Also, applying the Jacob index to observe or observed data can improve the efficiency. This resource will help us to get a more handy and precise end-to-end unsupervised playstyle measure. Also, we can bridge the gap between distance similarity and human cognition in playstyle. Besides, we have a new tool to quantify policy diversity. I prepared some Q&A. First question, how about incorporating macro actions to playstyle? Macro action is about a sequence of actions without the interruption in the action distribution. My answer is that if you want to include macro action to discrete playstyle, you can change the distance of policy to a macro action version, like the string distance or DTW, time series distance, or just make the action to be a multi-dimension. That's all possible. Just keep in mind that discrete playstyle just separate the action distributing distance over different states, and these states should be comparable. For another question, are there some applications of playstyle that mentioned previously? That is one important topic in my study. If we can measure and define playstyles, then we can try to express or create new styles that follow these measures. For example, in imitation learning, we can check whether an agent is really learned from the desired behaviors. In previous, we usually check the agent score. But how the agent really learned from the demonstration is not clear. Also, diversity can help us increase exploration. Then since we have new measures, then we can control the agent to explicitly increase this diversity. Also, in multi-agent cell play, we can maintain the agent diversity in the agent pool to make the training content or the training experience more diverse and across different tasks. And so on. I believe playstyle in general is a now well-explored domain and has many research potential in the future. Overall, thanks you for listening. If you can give a star to our GitHub repo, then it will be helpful to us. Thank you for listening again.